Hi students, welcome back. This is Madhu Dharmapuri, and in this lecture I'm going to start a new chapter, right? And in that I'll start with what is magnetic field and what are magnetic field lines, right? So before we go into the details of this, first let us see what is the concept of this magnetism, right? As we all know that a magnet is a source of magnetic field, right? It does attract some magnetic materials, right? We used to play in the sand when we were in the childhood by taking some magnet and keep playing with the magnet, so that all the small magnetic material particles used to attract to this magnet, right? And we are all familiar with the bar magnet having certain length. And we are all familiar with the poles of the magnet, north pole and south pole. And unlike poles attract each other, like poles repel each other. All these things we know regarding magnet, and these attractions and everything are because of magnetic field presence, right? So in addition to this, there is another source of magnetic field was discovered in the uh, early 19th century. Before that discovery, it was thought that electricity was separate branch of science and magnetism is separate branch of science. But in the early 19th century, Oersted discovered that even moving charges or current carrying conductors produce magnetic field, and it was confirmed, or it was discovered by him by moving a small compass in the neighborhood of current carrying conductor or moving charges, and he could see the deflection in the compass needle, just like we see the deflection when it is moved in the magnetic field or in the neighborhood of magnet, right? The same kind of deflection was observed when it was moved in the neighborhood of current carrying conductors or moving charges. Then he said that moving charges and our current carrying conductors are also source of magnetic field, just like a magnet produces magnetic field. And after this discovery, electricity and magnetism were thought of not separate branches of science. They are together, and we nowadays we are calling it as electromagnetism or electricity and magnetism. Electromagnetism. Okay, so what are the sources of magnetic field now? So magnet and moving charges, or you can say moving charge is nothing but a current flow, right? Current carrying conductor. Current carrying conductors are the sources of magnetic field. Right? So what is field? Field is some region actually in the space around magnet or in the space around current carrying conductor, some space. In that space, magnetic field is generated or produced only up to certain region based on the charge magnitude or current magnitude. or power of magnet, whatever. Right? So it is a field, but how much is the strength? What is the magnetic field? Just like we see in the electric field, we find out electric field strength at some point at a distance of charge, right? So in this magnetic field, we usually find magnetic field induction. See, actually, we most commonly we call it as magnetic field only. Determine magnetic field at this point, or find out magnetic field at this point. This way we use, but actually it is magnetic field induction. We represent it with magnetic. Sorry, we represent it with capital B. So magnetic field or magnetic field induction. Magnetic field induction represented with B. It is a vector quantity. Vector quantity. Units. You can say Tesla, Gauss, or Weber per meter square are the units for magnetic field or magnetic field induction. Right? The problems in the magnetism ask like find out magnetic field due to this current carrying conductor or this kind of current carrying conductor. Different kinds of current carrying conductors are there. They ask like find out magnetic field due to a straight current carrying wire or circular current carrying coil. So most commonly we use magnetic field only, but it is actually magnetic field induction. But actually magnetic field is some region, right? So remember this. Okay, in the region of magnetic field we find out magnetic field induction, or usually we call it as magnetic field. Okay, and I suggest you to read this chapter by comparing with the electrostatics, because there is lot of analogy between electricity and magnetism. Like charge in the electrostatics is analogous to north pole in the magnetism, right? There charge magnitude is analogous to pole strength of the pole, and electric field there and magnetic field here, electric flux there, magnetic flux here, right? So permittivity, electric permittivity there, of here magnetic permeability, epsilon naught and mu naught. So this is how you have to compare so that you would understand very easily. There are some similarities between those topics and magnetism topics. So keep comparing while studying this chapter, right? So that you get more idea and you will understand very easily. And remember all these topics for a very long time. Okay, so and in this lecture we are going to discuss about magnetic field lines, because in the space around a magnet or current carrying conductor, as I said, magnetic field is produced, and magnetic field induction is how much in that field, right? What is the amount of what is the magnitude of magnetic field? What is the direction of magnetic field? Because it is a vector quantity. So all these things we can get from magnetic field lines idea. Right? It gives the you can say a complete idea about magnitude and direction of magnetic field. Right? So what is magnetic field line? Right? It is a line. It is a line which is imaginary, right? Which is drawn in the magnetic field, along which a free magnetic north pole would move. See, magnetic field lines are imaginary lines. They are drawn in the magnetic field, along which a free magnetic north pole would move if allowed to. But this star you can see here, the free magnetic north pole is actually not existing. The magnetic monopole does not exist. Magnetic monopole does not exist. It is an imaginary concept. Right? So magnetic field lines are imaginary lines drawn in the magnetic field along which a free magnetic north pole would move. But in reality, there is no existence of magnetic monopole. Only dipoles are present. Okay, this is quite similar to the definition of electric field line. There we talk about electric field lines are imaginary lines drawn in the electric field along which a free unit, you can say a positive charge, a free positive charge is moving, test positive charge. So positive charge is analogous to north pole. This is how you have to compare. And one more analogy between electric field line and magnetic field line is that, see, electric field lines are called as electric lines of force also. But magnetic field lines are not called as magnetic lines of force. The reason is the force experienced by the charge in the electric field is along the electric field direction. But the force experienced by the charge in the magnetic field is always perpendicular to the magnetic field. This is the reason we call magnetic field lines, we do not call magnetic field lines as magnetic field lines of force. Okay, so remember this concept also. Now we will see some of the properties of magnetic field lines. Okay. Properties of magnetic field lines. Right. The first property is magnetic field lines form closed loops. They do form closed loops, but electric field lines do not form closed loops. This is a comparison. Okay, so what is the meaning of this? For example, consider a bar magnet with two poles, north and south. For example, if this is north and this is south, right? How do we draw magnetic field lines in the case of bar magnet? See, in the laboratory, we keep a bar magnet on a white paper fixed to the table at the center. Then we keep moving a compass nearby the magnet so that the needle deflection we will observe, and at that deflection point we keep drawing small lines, and later we will connect all these small lines so that you will get a magnetic field line, right? So this is how they represent. They look like. So for example, and what is the direction? So they always come out from north and enter from into the south. And inside, if you see, from south to north. Very important. Outside magnet, magnetic field lines, go from north pole to south pole. You can see outside. But inside magnet, magnetic field lines go from south pole to north pole. South pole to north pole. From here north to south and inside south to north, so that they form closed loops. Magnetic field lines form closed loops. This is the first property of magnetic field lines. Right? So now we will see second one. Second property is tangent drawn at any point on the magnetic field line gives the direction of magnetic field at that point. Magnetic field at that point. Let me write it here. For example, if this is the magnetic field line, and at this particular point, the tangent drawn is a magnetic field direction, and at this particular point, the tangent drawn is magnetic field direction. At this particular point, tangent drawn is magnetic field direction. So this is how the magnetic field direction is known from the tangent drawn on the magnetic field line. Tangent drawn at any point on the magnetic field line gives the direction of magnetic field at that point. This is the second property. Right? And third one, we can say, let me write it here. Magnetic field lines do not intersect each other. If they intersect, what will happen? If they intersect, at the point of intersection, magnetic field would have more than one direction, which is not possible, that they do not intersect each other. If they do intersect, at that particular point of intersection, magnetic field would have more than one direction, which is not possible. See, you can see, for example, if this is one magnetic field line and this is another magnetic field line, they are intersecting here, and at this particular point, it will have two directions. Magnetic field point will have two directions, which is not possible. Right? If this is one and this is two, say one first line and second line. So at the point of intersection, you have two directions for the magnetic field, net magnetic field. Okay, so this is not possible. This intersection is not possible. Okay. And the fourth point is about the magnitude of the magnetic field. Closer the magnetic field, lines, stronger the magnetic field. What does this mean? If field lines, that is magnetic field lines, if magnetic field lines are closer to each other, magnetic field is stronger. And if magnetic field lines are far apart, then magnetic field is weaker. This is the meaning of this. Right? How do we represent this? See, for example, if these are the magnetic field lines, right? And we have 2 points here. For example, this is X and this is Y, right? So magnetic field at X is greater than magnetic field at Y, because here the magnetic field lines are very close to each other, so stronger the magnetic field. Magnetic field lines are far apart from each other, so weaker the magnetic field. This is greater than this. This is the fourth point. Okay, so now we will see fifth point. See, if this is the case, we call it as non-uniform magnetic field. Okay, so here magnetic field strength is larger, magnetic field is weaker, so non-uniformly distributed. Okay, so fifth property of magnetic field line, fifth one is straight, parallel, and equidistant magnetic field lines represent uniform magnetic field. Means everywhere magnetic field magnitude and direction is same. That means these are the magnetic field lines, equidistant, parallel, but straight. So if this is point X and if this is point Y, for example, if this is some X and this is some Y, you will find that magnitude at Y and X will remain same. Uniform magnetic. If field lines are straight, parallel and equidistant to each other, you can say that the magnetic field is uniform. Okay, so these are the very important properties of magnetic field lines. Now we will see some of the diagrams of magnetic field lines, how magnetic field lines can be drawn for current carrying conductors and current carrying loops. Okay, of a magnetic field lines. First, consider a current carrying wire in which I current is flowing. Right? As I said, current carrying wire is a source of magnetic field. Right? So magnetic field lines drawing is like you have to use your right hand. Thumb represents the current direction and the other four fingers represent the magnetic field direction. Wrap your fingers in such a way that, see, so this is the current direction. Wrap your fingers in such a way that your fingers represent the magnetic field direction. So here it will be like this, concentric circles. What are the directions? This side it is this, and it goes inside. So this is how the magnetic field lines for current carrying wire. Right? So another one, if you have a current in this way, and this represents current inwards this way. Right? In general, this represent inwards and this represent outwards. Right? So the current is now towards into this board. This magnetic field lines are this way. They are going like this and this. Right? So this is how you have to draw. They have to be closer. So that what is the direction? Right? So this way. Right? So they come like this. Right? And another one is current loop or coil. Right? So it is like current loop is like this is current loop. Let me draw it here. This is current loop. And if current direction is this way, right? So current direction is this way. It is like you can see this is current loop. For example, this is a wire, closed loop, right? Some current is flowing. So if you see this in this position, right, the current direction, this side is towards me and here is towards that side. This is the way of current direction. Okay, right? So how do you draw magnetic field lines for this now? See, for example, if you check here, what is the current direction? It is going like this. What is the current direction this side here? Towards the board, because the current direction is this, towards the board. So the magnetic field lines should be in this way. See, the thumb represents towards the board here, in this way. It comes out like this, right? So this is how magnetic field lines. So they go up inside, right? So this one, and it comes down here, right? Similarly, what about this side? The current is going this way here towards you, right? So the field lines will be again coming out like this and like this, right? So inside again, upwards, right? So coming down. So they go like this. Here also, upwards, right? That means they go like this, they enter like this. Right? So they go like this and they enter like this. This is exactly like if this is a bar magnet with north and south poles like this, so that its magnetic field lines will come out from north and enter into the south, and inside this magnet it is south to north. Okay, inside this magnet south to north. See, they form closed loops. Magnetic field lines form closed loops. Right? So outside the bar magnet, magnetic field lines are north to south, and inside bar magnet, magnetic field lines are south to the north. Exactly same as the magnetic field lines due to a current loop, which means that this current loop acts as magnetic dipole, which means that this should have two poles, right? So that poles will be identified. Poles are identified using clock face rule. Okay, so poles are identified using clock face rule, because we cannot simply say this is north and this is south, as in the case of bar magnet, right? So what is that clock face rule, and what are the poles of north and south for this current loop if it is acting as a magnetic dipole, right? So for this, the clock face rule is the clock face rule, right? It is very simple that if the current direction is clockwise, the current direction is clockwise direction, of current, for clockwise direction of current, it is south pole. Okay, and for anti-clockwise direction of current, so for anti-clockwise it is north pole. For clockwise rule, the phase from which the current direction seems to be clockwise direction, that is south pole. For this case, it is from bottom because current direction is this way. And the phase from which current direction seems to be anti-clockwise direction, that phase is north pole. So this one. Okay, so this is how we can draw magnetic field lines for a current loop which is acting as a magnetic dipole. Okay, hope you have understood. If you have any doubts regarding this lecture, you can put your doubts under the comment section. Thank you very much.